collection of nitrogen gas molecules is at a pressure of 100,000 pascals, a temperature of 25 degrees C, and is held in a box with a volume of 2 cubic meters. Answer all the following. This is a problem involving the ideal gas law and the first law of thermodynamics. Ironically, even though these subjects are mathematically among the easiest things you will do in an introductory physics course, students tend to get the worst grades in these sections. I will not be spending the time while solving this problem to derive all of these results. Instead, I'm just going to simply list the appropriate equations that we have to deal with in solving the problem at hand. The first one of these equations is the ideal gas law. This is the one that says pressure times volume is equal to the number of moles times the ideal gas constant, capital R, times the temperature T. The ideal gas constant, as we recognize, is simply a unit conversion factor. If we had used the number of molecules instead of moles, and if we had recognized that temperature is implicitly measuring an amount of energy, then in fact there would be no need. Our ideal gas constant that we'll use in this class is accounting for the fact that we will use proper units for pressure and volume, so that the left-hand side of the equation will be in joules. However, on the right-hand side, we'll make two errors. One of these is moles, and the other is to use Kelvin. In these particular form of units, the value of the ideal gas constant will be 8.314. PV equals nRT is in fact the most complex formula that we deal with in an entire first semester physics class. The reason is that the pressure, volume, number of moles, and temperature can all in principle vary, meaning that this is a relationship among 4 independent variables rather than the relationships among 2 that we began the class with. This makes the possibilities available to PV equals nRT numerous. Because this formula is in fact so complex, in high school classes, a PV equals nRT problem simply consists of being given 3 out of the 4 unknowns and asked for the 4th one. Nothing could be easier. However, in this class, we need to couple the concept of PV equals nRT as an equation relating the state variables of an ideal gas to the first law of thermodynamics, which states that the change in internal energy of any system, including ideal gases, can come from 2 sources. One of these is the heat flow that goes into the system, and the other one is the work that comes out of the system. In most physics textbooks, we consider W to be the work done by the system, whereas unfortunately in most chemistry textbooks, we consider W to be the work done upon the system, in which case there would be a sign change to be Q plus W. We also recognize a fact well beyond your high school class, that the temperature itself is uniquely related to the translational kinetic energy of a given molecule, in that the average translational, not rotational, just translational kinetic energy of one molecule is related by a factor of 3/2 to the temperature. Now, since we're going to be dealing with the temperature in Kelvin, and translational kinetic energies should like to be in joules, we'll introduce another constant. This constant goes by the letter K, and it's the Boltzmann constant. Similar to the constant R, it's a unit fixer. K in this case will leave behind the appropriate units of joules, having killed the units of Kelvin. Comparing to the result for R, you'll see that the only difference is that K does not account for using moles instead of the number of particles. In this case, the relationship between K and R is that K is R divided by Avogadro's number, which produces a result of 1.38 times 10 to the minus 23 joules per Kelvin. Since we understand that translational kinetic energy is 1/2 mv squared, we can actually solve the formula in red to find that the average value of the velocity squared is going to be equal to 3 times the Boltzmann constant times the temperature divided by the mass of a single molecule of the gas at hand. This quantity would be in meters squared per second squared and doesn't give us a proper velocity relation. And so what we do is we take a square root on both sides of the equation, and this quantity is defined to be the root mean square velocity. The formula we have for the root mean square velocity is exactly correct. However, it contains two tiny numbers. It contains the Boltzmann constant K, which is tiny. It also contains the mass of a single molecule, which is tiny. We can multiply inside the square root by a factor of Avogadro's number, both numerator and denominator, to get a simpler and more pleasing form, so that the Boltzmann constant has turned into the ideal gas constant. And instead of the mass per molecule, we've turned into the mass per Avogadro's number of molecules, which is known as the molecular weight, for which we'll use a capital M. The second formula has numbers that are closer to things that you would normally deal with without the 10 to the minus 23s floating around. While dealing with solids and liquids, we found relationships between the amount of heat that would flow into or out of a system and the temperature change that would result from this. Typically, this was known as the MCAT formula, and we would use the mass to denote the quantity of material. Here that seems kind of silly. We will not use the mass of the gas in question, but instead we will use the number of moles. For this reason, rather than a lowercase c, which is the specific heat, we use the molar specific heat, capital C. When dealing with an ideal gas, this formula has a problem. The reason comes from the first law of thermodynamics. The first law of thermodynamics states that the change in internal energy, the internal energy comes from the temperature, is related not only to the heat flow but also to the work. Therefore, depending upon whether the system does work as the heat flows in or out, the amount of heat necessary to produce the same temperature change will be different. That's just conservation of energy. So we're going to denote two special cases before we get even more detailed by moving on to engines and refrigerators. The first case will be when the volume is held constant. I can denote this by Q subscript V on the left, which is the amount of heat that flows into our ideal gas when the volume is held constant. If, on the other hand, we hold the pressure constant, let's imagine that for a moment. As you increase the temperature of a system, you might expect that the pressure would increase. However, if we allow the system to change its volume, we can maintain the same pressure during the process, meaning that some of the energy went into increasing the volume, thereby doing work. As a result, the amount of heat necessary to flow when the system is kept at constant pressure still has an N and a delta T, but the proportionality constant is going to be different, and the proportionality constant will be the molar specific heat at constant pressure rather than the one at constant volume. These two relationships have been required to relate heat to the change in temperature because heat is not nature's proper indicator of the temperature. The proper indicator of the temperature in any system is the internal energy. And any change in internal energy can be related to a change in temperature via, number one, the proportionality constant of the number of moles, and number two, some constant. As it turns out, the case where delta U and Q have the same amount is when W is 0. W is 0 when the volume doesn't change, and so even though the V on C capital V came associated with a heat formula, it is in fact the proper proportionality constant between a change in internal energy and a change in temperature, regardless of whether you keep the volume constant or not. One more detail in our cursory summary of the equations that surround the ideal gas law as we deal with gases. And that is that these two constants, C sub V and C sub P, actually depend upon the type of gas that you are using. The reason is that the temperature is related to the translational kinetic energy. And although for an ideal gas there will be no potential energy, in addition to translational kinetic energy there might be rotation, and that will affect all of these proportionality constants. Monatomic gases, which I use the word mono here, cannot rotate. Therefore, coming from our expression relating translational kinetic energy to temperature, we find that C sub V is going to be 3/2 times the ideal gas constant. Diatomic gases can rotate in two possible ways. Therefore, we get two more factors of 1/2 R for a total of 5/2 R. And in some textbooks, although not all, we will assume that polyatomic gases are frequently such that they can rotate in three ways and vibrate in one way, and so we'll use 7/2 R. In real life, these parameters are perfect for a monatomic gas, awfully good for diatomic, and they actually sometimes work with what's written here for polyatomic. But we're going to keep the whole table since it does appear this way in some textbooks. C sub P must be larger to account for the fact that, in addition to heat going into temperature, heat can also be used to generate work. What happens is that C sub P is always larger by one factor of R, so we'll have 5/2 R, 7/2 R, and 9/2 R for the constants C sub V and C sub P. This collection of equations, when you understand it fully, will be able to solve every question we've been asked in the problem at hand. So let's begin with Part A. Part A asks us how many molecules are in the box. Molecules are most directly related to the number of moles, and so we're going to begin this part of the problem by noting that PV equals nRT is one of those high school-like problems. You've been given PV and T, and you're asked for the number of molecules. So we can solve to find that the number of moles, not molecules, is going to be equal to PV divided by RT, and substituting in the values that we know, we'll be able to solve the problem. Notice that I've only put in PV and R so far. The reason is we need to pause when we handle the temperature and think for a moment. If this formula were to involve a difference in temperature delta T, we'd be able to solve this using either Celsius or Kelvin because differences in temperature are the same in Celsius or Kelvin. However, in the formula PV equals nRT, the T stands alone. As a result, we need to put the temperature in Kelvin as the only route to getting the correct answer. So our temperature is going to be the 25 degrees Celsius plus 273 in order to get this quantity into kelvins. Plugging in all this information, we'll be able to solve for the number of moles. The result is 80.72 moles. This result is not yet the number of molecules, it's merely the number of moles, and so in order to get the number of molecules, we'll need to multiply the number of moles by Avogadro's number, yielding the result 4.86 times 10 to the 25th. Part B asks us for the average translational kinetic energy of one of these molecules. Well, we remember that average translational kinetic energy is related to the temperature directly, and so the formula is 3/2 kT. Looking carefully at this formula, we once again note that the T stands alone. It is not a delta T, and so therefore in order to get the correct answer, the T must be listed as Kelvin and not as Celsius. 6.17 times 10 to the minus 21 joules. To get the root mean square velocity, we can use one of two formulas. The first relates the RMS velocity to the temperature using the Boltzmann constant and the mass of an individual molecule of the gas. The second formula uses Avogadro's number to change both the Boltzmann constant into the ideal gas constant and the mass of one molecule into the mass of a full mole of molecules, which we'll call capital M. I'm going to use the second of these two forms since the numbers are a little bit simpler. The 3 represents the fact that we're in three-dimensional space. The ideal gas constant is 8.314. And since the T stands alone, the temperature will be in Kelvin, which is the 25 degrees C plus 273. The gas is nitrogen, and what we need to know about nitrogen is first that it contains 7 protons and 7 neutrons for a mass of 14, and second that it's diatomic, meaning that 2 of these 14s will go together to make a single molecule, making 28 grams per mole. In this class, we don't use grams as our mass, we use kilograms. And so 28 grams as the molecular weight is equal to 0.028 kilograms in a single mole. This will allow us to get our RMS velocity in the units of meter per second. The result is an RMS velocity of the nitrogen molecules in air of 515 meter per second. You might ask for a moment whether it hurts to be slammed in the face continually with nitrogen molecules at 515 meter per second. The answer is that doesn't hurt because your body has an internal pressure. If they ever disappeared, then that would hurt. Part D asks us for the internal energy of the system. Well, what we recognize from the formulas on the previous page is that the change in internal energy for an ideal gas is equal to the number of moles times the molar specific heat at constant volume times the change in temperature. And this is true regardless of how the gas changes its temperature, whether it does it at constant volume, constant pressure, or even by another means. The problem at hand, however, does not ask us for the change in internal energy. It asks us for the internal energy. Many textbooks would never ask this question, and others would. Why is that? When we defined an ideal gas, we said that there are no potential energies involved, i.e. no interactions among the gas molecules. There is no gas in nature for which this is actually true. Even helium, the most ideal of gases available to us, when made cold enough, will form a liquid, and so its internal energy cannot be obtained simply by summing over the kinetics. For this reason, some books would never dare to ask you the total internal energy of a system. Others go ahead and say that if an ideal gas is an idealization of something that could occur in nature, then the formula for the internal energy would be well defined by simply removing the deltas from the previous formula. I'm choosing here to assume that this is going to be allowed by us. The constant capital C sub V depends upon what kind of gas we have. If it were monatomic, it would be 3/2 R, diatomic 5/2, and polyatomic roughly 7/2 R. Because nitrogen is diatomic, the C sub V for this problem is going to be 5/2 times the ideal gas constant. The temperature stands alone in this formula, and the number of moles from the prior part of the problem is 80.72. Putting in all these factors allows us to calculate the total internal energy of 500,000 joules. In part E, we're asked to calculate the amount of heat that is required to raise the temperature of this gas from 25 degrees C to a final temperature of 35 degrees C if the volume is not changed. When the volume is not changed, we'll be using the heat for a constant volume process, which is going to be N times C sub V, this is where the V came from for volume, times the change in temperature. Using our 80.72 moles from the previous step, we can combine this with the C sub V, which for any diatomic gas, which nitrogen is 5/2, the ideal gas constant. And then finally, the change in temperature can be evaluated using Celsius, so we'll take the 35 minus 25. The result is an amount of heat for a constant volume 10-degree process of 16,780 joules. If instead we forced the system to have a constant pressure as the heat was added, it's actually going to require more heat in order to achieve the 10-degree temperature change, because the formula for the amount of heat at constant pressure is the number of moles times the specific heat at constant pressure times the change in temperature. We'll be able to use the 80.72 moles, but when we reference the specific heat at constant pressure, we're going to have the larger number of 7/2 times the ideal gas constant. And this gives us the result for the heat necessary at constant pressure to achieve a 10-degree temperature change of 23,450 16,490 joules. Note that when we kept the pressure constant, it actually took more than 6,700 additional joules of heat to cause the temperature to go up by 10 degrees. The reason is that the means by which the pressure was held constant was allowing the system to expand. The expansion did work, and the energy for that work was supplied by the extra heat that we put into the system. Finally, for the last part, we're asked to calculate the change in internal energy, which always follows the same formula. Number of moles times C sub V delta T. Given the number of moles, the C sub V for a diatomic gas, and a change in temperature of 35 minus 25, we see that the change in internal energy is equal to 16,780 joules. Let's think about this result for a moment. Remember, back in part E of the problem, we calculated the amount of heat assuming that the volume was a constant. When the volume is a constant, there's no work done. When there's no work done, the first law of thermodynamics, delta U is Q minus W, simply reduces to delta U equals Q, and so every one of those 16,780 joules went into the internal energy. However, when we did a constant pressure process instead, the system expanded doing work. So we put in 23,490 joules so that 6,710 joules went out as work. We can use this work, and you may use it every day getting to school if you drive a car.